So here to briefly introduce the content of this section, let's say in one sentence, what happens if you have two vectors A with components A1, A2, A3, and vector B, B1, B2, B3. So we have two vectors and we want to define an operation that is calculating the inner product, the dot product between vectors A and B. And if you want to finish this section in one sentence, this is going to be the dot product is just going to be the components multiplied and you take the sum. So we have A1 B1 multiplied plus A2 B2 multiplied plus A3 B3 multiplied. Okay. So if you know this equation, you'll be able to solve most of the questions on MATLAB. But if you look at this equation, okay, this is a kind of operation that gives you a scalar, right, from two vectors. So how are we defining this? So that's the rest of our section. Recall. So if we have vectors A and B, actually, when we do the addition, we actually throw these two vectors into a operation that we call addition, right? So it's a white box in the sense that you know everything that happens in this white box, right? But suppose you have no idea about vector multiplication or scalar multiplication or addition, then you can say due to some magic, but following some rules that we are producing this output as A plus B. Right? So it's essentially an operation that combines the information of two vectors and give you a new vector, right? And then also, if you think about the magnitude operation, it's really similar, but we only have one input as a vector. And when we take the magnitude, eventually we get a scalar, right? So that is producing us the magnitude, which is a non-negative number, which is a scalar. So the addition is playing with two inputs and producing one output as a vector. Magnitude is saying, okay, I have one input as a vector, but I produce one scalar. Right? So here we want to define. Let us define an operation as follows. We have the inputs as two vectors, A and B vectors. We want to do some operation which we will specify, which we have already specified right here, that we are returning a scalar. And of course, we want to be really clear about the meaning of the definition. Okay, so what does this actually give us? And here comes the idea. So the dot product formula is at the beginning of the section, where you just do component-wise multiplication of and then do the addition, right? So the geometric meaning, the geometric perspective, we will represent as follows. So we have two vectors, A and B, right? So they are here, in general, they have distinct directions, right? But usually there will be an angle that's cut between these two vectors because essentially now they are in different directions. Okay? So there's an angle theta right here. So theta is let me just put an angle without an arrow. So theta is the angle that's cut between two vectors. So if you think about two vectors in 3D, no matter how you position these two vectors, the angle between them is always what? It's always less than 180 degrees, right? It's always between 0 and pi, right? So now, what do we do here? So we know the length of each vector is the magnitude, right? So that's the magnitude of A. This one is the magnitude of B. B. I want to draw the bracket nicely, but okay, that's good enough. Now we want to do the what do we want to do? We want to do the projection of the head of B onto the vector A. So here I'm drawing the perpendicular dashed line starting from the head of B and perpendicular onto A. So this is called the projection. So we know the angle cut between the vectors are the cut between the vectors is theta, right? So we actually form the right triangle, and this edge right here is actually the adjacent edge of the right triangle to the angle theta, right? So you know this length is what is the hypotenuse times cosine, right? Now, let's suppose we use this length as the magnitude, but we use the direction of A, right? That will define me a vector. We shall put on the right. So A, B, projection. This vector. This is a vector that has magnitude B, the magnitude of B times cosine theta, that's the magnitude of this solid red vector, and the same direction as A. So basically, here this is essentially saying, okay, we have the vector B that's in a different direction from A, right? But we want to know the effect of this vector B along the direction of A. So what's that going to be? So here, the way that we measure this is by doing the vector projection. Is that we do the projection down to the direction of A by doing this orthogonal perpendicular projection, right? So that results as a vector. And here we define the dot product. We obtain an operation as follows. So it's going to be called the dot product. Here we input two vectors A and B, and here we output the calculation of the magnitude that we computed just now from the vector B, and we multiply by the magnitude of A. So if you rearrange the order of calculation, this is exactly the magnitude of A times the magnitude of B times cosine of theta, the cosine of the angle that's cut between these vectors A and B. So the geometric perspective is always a little bit less intuitive. The arithmetic perspective that we have introduced at the beginning of the session is a little bit different. It's a little bit more straightforward. But let's put that down also. The idea that's arithmetic. Arithmetic it's a little bit more straightforward. That's A dot B equals A1 B1 plus A2 B2 plus A3 B3. So here, let's do some formal definition. So denote the dot product. So we have written the notation for twice, right, at the beginning and right above. The notation is A starting with B. It's a solid dot. And the calculation, actually, the definition we're gonna stick to is the arithmetic, excuse me, the geometric definition. So the magnitude of A times the magnitude of B times cosine theta. The theta is the angle cut between the vectors. So here, starting from next class, we will continue, but the rest of the section is gonna be through the geometric perspective. We will continue through the geometry. Example. So we begin with the fundamental one. So vectors A and B. Have magnitudes 4 and 6, and the angle cut between the vectors is pi over 3. Then we want to calculate the dot product, okay? So by definition, so that's the magnitude of the first vector times the magnitude of the second vector times. Now the definition is that it's a cosine of the angle cut between the vectors, right? So it's cosine of pi over 3. So direct multiplication. But now we just need to watch out for the cosine, right? So for those special angles like pi over 6, pi over 4, pi over 3, pi over 2, 0, and so on and so forth, you do need to know how to calculate cosine and sine. So that this is 4 times 6 times cosine pi over 3, so half. So essentially, this is going to be a 12. So if you want to somehow review the cosine for special angles, you can draw the triangle out and so here, okay, so this triangle, I probably have the angles to be pi over 4, so that looks a little bit off. Suppose I'm having pi over 3, pi over 6, and pi over 2 right here, then if you recall the shape, it's like 1 at the adjacent edge and 2 on the hypotenuse and square root of 3 on the opposite edge of this angle right here at pi over 3. So now cosine is what? Cosine is the adjacent over the hypotenuse. That's 1 over 2. Okay, so if we just directly apply the formula, it shouldn't be hard. Okay, so now geometric properties. Of the dot products. So basically, we'll give the formulas, but then we just argue they're true by doing the geometric perspective. Okay, so now we have A dot A. So we have, if we have two identical vectors dotted with each other, then we know that the magnitudes are gonna be the same, right? But now there's a cosine of the angle cut between them. Now, what's the angle between two vectors that are identical? 0, right? So cosine of 0 is something really simple. It's just gonna be 1. Okay? So then you will just have the magnitude of a squared. Right? And the second property is that the dot product is commutative. So basically, when you have A dot B and B dot A, they're gonna give you the same scalar value. Because when we talk about angle theta, that's actually the angle cut between A and B. So if you interchange the order of this operation, that angle is still gonna be the same, right? And then, of course, the order of A and B magnitudes multiplied, that order doesn't matter at all. Because it's just a scalar multiplication. So our dot product is commutative. Item 3, so if you have a 0 vector starting with some vector A, what does it give you? So if you think about it, if you just do the definition, there's the magnitude of the 0 vector, magnitude of the vector A, and then cosine of the angle cut between them. But we don't really need to worry about that angle, we don't really need to imagine that because the 0 vector has a magnitude of 0. Right, so we have a 0 multiplying by some other numbers, it's always gonna be a 0. And now, item 4 is gonna be a complicated one. So number 2 is saying we can commute, right? But item 4 is about distribution. So if we have A plus B as a sum, starting with the vector C. So we can do this distribution so that this the sum starting with the vector is gonna be the dot. Just you add up the individual dots. So A plus B dot C is gonna be A dot C plus B dot C. And if you combine item 2 together, that will give you 2 other quantities. So you can interchange the order of your dot in the first place. So this is gonna be the same as E dot A plus B. And then, so the sum on the right hand side in the bracket can also be distributed, okay? So it's gonna be C starting with A plus E dot. Right, now, so this one is not so simple to argue by the geometric perspective. So let's take a look. So let's say we have vector C right here. But then now we have a sum, right? We have A plus B. So let's put them together as a triangle. So we have the tail and the head of the vector A. And then we stack the tail of B at the head of A. So what do we know? We know, okay, A plus B is gonna be the third edge of this triangle, right? So this is A plus B. Right, so now let's just concentrate on the first equality here. So basically we're just saying, okay, the sum starting with C is gonna be the individual vector starting with C and add up, right? So now A plus B dot C is gonna be what? So we just recall that for a vector starting with another, we want to do that projection of that first vector onto the second, right? So we have A plus B right here. So what we want to do is we use the head and then we do the projection down to the vector C. And then we recall that this line segment is gonna be the magnitude. Right here. So this length is exactly so I'm thinking. So we don't really need too many angles. So let's call it alpha. This is alpha. So that's A plus B cosine of alpha, right? So we have A plus B, that's a vector, and this vector between C, there's gonna be angle alpha, right? And then we use this quantity to multiply by the magnitude of C, that will give us the left-hand side. So that's what it is. Okay. All right, so that's the idea for the left-hand side. Now, for the right-hand side, we're gonna do something in a similar fashion, because this is the geometric perspective. So C, A, B. But now, if you think about this individual vectors A and B, then the A part is going to be, relatively speaking, more straightforward, because A and C, they have the same tail right here, right? So when you do the projection, it's going to be this one. So the head projecting down. Okay. And let's call this angle theta. So this part right here, I'm going to put it in red. It's going to be the magnitude of A cosine theta. Okay. Right now, so that's A dot C. Okay, so we use this quantity to multiply by the magnitude of C. So that's simple. Now for B, what do we do? So this vector B, we just want to get another copy of C. So basically, if you recall the parallelogram rule, we just establish a parallelogram, which is just saying, okay, for the vector C, we're just gonna do the parallel copy, which has the same magnitude, right? Same length. It just goes to the right, like that. Okay. And now, so B and C, they have now the same tail, and I'm gonna define this angle to be phi. So if I do the projection here, so this is from this point going down to the dashed vector C in red, right? So that's another projection. And this part is B cosine phi, which is the length of the projection that we want for beta C. Sounds good? So we almost to the end of the right-hand side. Okay, so we individually expressed the projection onto the vector C for both A dot C and B dot C, right? But then here comes the punchline. So we want to somehow argue that this piece, adding this piece, eventually agrees with this piece. Right? So this is a geometric thing, and in a way, in this figure, you may say, okay, it looks obvious, because if I do this projection all the way down to this point, when this big red dot, you see these two red dots, they are exactly the same point, right? Because that's the head of B, or the head of A plus B in the figure. So when these 3 points are on the same line, actually. So now think about this. So A and B, these two vectors, yeah, let's look at the monitor right here. So behind me. So if we have vector A and vector B, what? Oh, I think I touched something. So I do. Oh, sorry. Wait. So let me touch it again. Okay, so this vector, so if A and B are in the same plane, right? If A and B are in the same plane, then this point, this red point, is exactly within the plane. So if you do the projection onto the red vector C, and then down to the parallel black vector C, so this point, and this point, they are actually on the same line, right? So the point here, let me put in the cross. Let me put a cross. So the black point, black cross right here, and the purple cross right here, they're exactly the same point, right? So this red dot within the plane, doing the projection, doing the orthogonal projection all the way down here, that's the same. Oh well, on the left hand side, this is directly projection down all the way here. That's purple. Here, if I do this projection onto the red one, and then continue this point down, perpendicularly to the black vector C, it's going to be the same point, right? So these two are the same. So that looks obvious if everything is in the two-dimensional space and within the plane. Now, if we were on a three-dimensional space, it's a bit different because I'm just gonna sketch it right here. So that's gonna be the same length, right? So now I want to mention that even if this red dot right here, even if this one is outside of the plane in front of you, this projection down to the red C and then black C will still end up with the same point as this point. Okay, let me illustrate that in another figure. So now we're gonna do a three-dimensional illustration, which is slightly different, but this imagination is very important. Okay, so three-dimensional. So that's the vector C right here. That's the vector A. Right. So now these are the two vectors we always find, and they're within the same plane, right? But now let's just imagine. So we don't really draw that B because that will give us that point within the plane. But just suppose that these two will form a plane, and then that red dot is not on that plane. So it could be somewhere like right here, high above. Okay. And what have we done? We actually firstly we did a parallel copy of vectors. Not super parallel, but we did a parallel copy of C right here, right? And what have we done? We actually, so the red vector and the red dot, so that forms you a plane, and you can do the orthogonal projection onto this point right here, right? So that's this point. This is a smaller red dot. Okay. And then you project down to the black sea, which is actually this one. Right here. And that forms you that black cross. Okay. So now our question is mainly this. So if I start at the red point right here, and I want and I do the projection down to the black vector C all the way here, will I end up with the same point? This projection point in purple is going to be the same as the black one. Okay. So actually, they are going to be the same because we have a really nice argument in the sense that the plane that you construct doing the red dash projection and the black dash projection. So these two lines actually form your plane, right? So what do you know? You know the red one is perpendicular to C. The black one is perpendicular to C. So that entire plane is perpendicular to the red dashed vector C and the black vector C. Right? Does it make sense? So basically what I'm saying here is that the two circled dashed lines, they are perpendicular to the vector C. So later you will see that if you have this purple plane, then the vector C is actually the normal vector, the vector that's perpendicular to the plane that's in front of you. Okay. So now, so if we can imagine that this entire plane is perpendicular to the vector C in red and in black, then you actually know that this line segment connecting the red dot and the cross is also perpendicular to C. Okay. So that tells you the black cross and the black cross here and the purple cross here, they are exactly the same point. Okay. Actually, is the geometry clear? So just to mention that this kind of illustration is not really required, but this is definitely important for you to understand what's going on. So basically, we're just saying, okay, for this part, we end up at this point. That's critical for the dot product evaluation. And for the right hand side, we start from this point and we end up with this black cross. Okay? Or you can say we start at this point and we end up at this black cross. Right? If we want to verify they are essentially the same within that equation, then we essentially want to verify that the black and the purple cross, they are exactly the same point on vector C. Right? Okay. So that's it. Geometry, very important. Okay. So now this is definitely so. Well, later you will see that the dot product is essentially really easy to verify in the arithmetic perspective, but in geometric perspective, it's a little bit it requires you to have some imagination here. So so essentially, this length also equals to a cosine theta plus b cosine b. Okay. So that's the thing that we verified. And on the right hand side, let me also just comment that A dot C is what? A dot C is a cosine theta times the magnitude of C. And B dot C is vector B, the magnitude cosine phi and magnitude C. Okay. And now you see, okay, for the right hand side, we just add up these two multiplied by the magnitude of C, and eventually that's the same as this, multiplying by the magnitude of C. So everything is good. Right. So this property. Okay. Now, using this property, we will be able to verify that the arithmetic perspective of the dot product is exactly the formula that we started this section. Okay. But before that, some examples. So what's I dot I? So if you have the unit vector in the standard basis, I dotting with itself is going to give you. It's going to give you what?
I squared.
Yeah, the magnitude of I squared, right? But I has a magnitude of 1. Right? So that should be a 1. And of course, J dot J is also going to give you 1, right? And K dot K is also going to give you 1. So let's draw the standard basis again. So for the standard basis, we have I, J, and K, right? But then that's Y. We now know for standard basis vector starting with itself is going to be 1, right? But what about just they dot with each other? So I dot J is going to give you. It should give you 0, right? Because this is going to be the magnitude of I, the magnitude of J, cosine. The angle cut between them is pi 2, right? So the x's are perpendicular to each other, so the angle cut between these vectors are pi 2. So that's 0. This is 1. This is 1. But now the ones will not really matter because these vectors are perpendicular to each other. Okay. So Ij dotting with each other is going to give you 0, and the same happens with the J and K and K and I and K. Remark. Dot product of 2 perpendicular vectors is 0. We say that vectors A and B. Well, let me just put the words instead of this. And B are orthogonal if A dot B. Yeah, so let me put it in outline. So if A dot B equals 0. Okay. So whenever you have 2 perpendicular vectors, you can always say, in another word, that they are orthogonal. And also, we realize that in a formal property that 0 vector starting with anything is 0, right? So 0 vector is considered orthogonal to all other vectors. Right. Now we are able to verify the arithmetic perspective of the dot product from the geometric. Okay. So here, if A equals to the vector with components A1, A2, A3, and B equals to the vector with components B1, B2, B3, then we know that A dot B equals to the components multiplied respectively, and then add up the products. So this is actually not so hard to see. So let's do the proof. We have, so that basically we just have the vector forms of the well, the tuple form of the vectors, right? We just write them in terms of the standard basis. Okay? So we have A dot B. So A is what? A is actually A1I plus A2J plus A3K. Right? And now for vector B that we're dotting, we put it in the bracket also, it's gonna be B1I, B2J, B3K, right? So now you see why we introduced the rule, the property of commutative dot product and also the distributive property, right? So the first step we can do the distribution of the first bracket. Okay? So we can write it in terms of three parts. So A1I starting with the rest, the entire B. Plus, so now vector A can be distributed into three components, right? So since I do have an iPad that I'm using, so I can cheat by copying the vector B that I have instead of, yeah, so let me do it nicely so that I don't have to erase anything. Copy, paste. Paste. So indeed, I can just distribute the first bracket into three terms, while I'm keeping the second bracket as a copy, right? And now, so far so good. The distribution, fine, right? Okay, now we can do the further distribution, but we don't really have to write everything down because now this is going to be easy if we just distribute the second bracket. So what do we know? We know I dot I is a zero, I dot I is a 1, right? I dot j is a 0, I dot k is a 0. So if you think about this is essentially, the first part is essentially A1I starting with B1I plus A1I starting with B2J plus A1I starting with B3K. And now you see A1, B2 is, it doesn't really matter because I dot J is a 0. I dot K is a 0. Okay. And you see, okay, I dot I is a 1 for this term. So you end up with A1, B1, right? Which is this term. So, and you do the rest the same fashion. So A to J dotting with B to J will give you J dot J gives you a 1, right? And K dot K gives you 1 right here. So essentially you see why we have only A1, A1, B1, A2, B2, A3 within the kind of result. Right? So this exactly comes from the fact that I dot I gives you 1, J dot J gives you 1, K dot K gives you 1, and zeros everywhere else. Right? And we're done. Remark. The geometric and arithmetic perspectives of the dot product are equivalent. and then to put them down in the same line. So basically, the geometric perspective is saying I'm multiplying the magnitudes and then times the cosine of the angle covered between them. This is the same as doing the calculation of A1, B1, plus A2, B2, plus A3, B3. As long as you know the components of vector n, right? Right, now, next properties. Well, we do have a few properties. Continued. So we have 1 through 4. Now this is property 5. So if you have C, a scalar multiplying with A, and then you dot with B. So the scalar multiplier, you can just take it off. Okay, so you can do the dot product first and then multiply by that scalar. So this is the associative of the scalar and dot multiplication. But then, of course, if you can take C out from here, then you can also just put C into the second vector. Okay, so that's the same as A dotting with CB. So this dot product is associative with the scalar multiplication. So that's actually pretty straightforward if you do both the definitions, the perspectives. Number 6, if A and B are non-zero vectors, then we do have a way to calculate cosine theta and eventually get theta. Okay. So basically from the equation above, we do know that cosine theta is exactly the dot product over the magnitudes. So this tells you, okay, if you have two vectors with the components, then you're able to use this formula to calculate the cosine value, and then you eventually get the angle. Okay, so now let's talk about the important concept of projection that we have been talking about. We just want to put everything down formally. Recall the geometric perspective so basically it says if you have vectors A and B, the geometric perspective says, okay, we need firstly the magnitude of the vector at the bottom, which is the magnitude of B, right? But then for the projection, what have we done? We actually start at the head of A and we do the orthogonal projection down to vector B, right? And then we got another vector actually along the direction of B, right here, as the shadow from A, right? So this is the vector that we get. So we label this as theta as the angle. And we know this solid red bar has a magnitude of a, well, I should say, okay, so if we do the projection down to the direction of B, So essentially, you see this as like a real line, right? This is the origin in a sense, and then this red thing, well, it could land on the right of the origin, it could land on the left of the origin. Right? So that's essentially a real number. But at least we know what that value is. That's actually A, the magnitude of A times cosine theta. And of course, if theta is too large, then this thing could be on the left-hand side, right? So now, the emphasis here is about the vector in red. So this vector is along the same direction as vector B and has magnitude as the magnitude of A times cosine theta. So I'm putting down the magnitude in the quotation mark in the sense that this value may not always be positive. Right? But then, like I said, if it were positive, excuse me, if it were negative, that just means this is just an opposite value. Okay, so this goes along the direction of the opposite of B, like something from here. So let me just put in the figure. Well, later I will put down figures, but currently let me just give some other descriptions. So this is the vector projection. Okay, the vector in red above is called the vector projection. Of A onto the vector B. Okay. So the direction we're looking at is actually this vector B. Okay. And then you start with A, so the projection is onto the vector. And the notation is something new, denoted by the following. So we write the first four letters of the projection, the word projection, and then we have a subscript that's telling you which direction you are projecting onto. And then what vector are you projecting? So that's A. So this is the notation. Note that this vector projection onto the vector B of vector A is a vector. Okay, so this is a vector along or exactly opposite the direction. Noting that projection of B, well, projection of A onto B has magnitude the magnitude of A times cosine theta and is along the same direction as B. We have a relationship. So we can express it out in the following quantity right here. So basically, the projection of vector A onto B is going to be the magnitude part multiplied by the direction part. And the direction is what? It's a unit vector along B, right? So it's going to be B over the magnitude. So notice that this cosine value from the earlier property is gonna be A dot B over the magnitudes of A. So we are able to simplify this expression. And so we just cover the vector projection, okay? So the projection of the vector A onto the vector B is just you're doing that orthogonal projection down to the direction of B, and then you will get a quantity that's representing the magnitude, which is a real number in front of the unit direction of the vector B. Okay? So the magnitude thing is A cosine theta, where theta is the angle cut between the vectors A and B. So we can replace the cosine by the inner product over the product of the magnitude. And then we can see doing the substitution, A and A, the magnitudes will be cancelled, they're common, right? So essentially you will see, okay, if I write everything in terms of B, it's gonna be this quantity times B. But well, that's one way to write it, but this way of writing it, where we keep the first bracket as the magnitude along the unit direction of B, right? So that's purple circle part. That's gonna represent the scalar projection, okay? Which just stands for the magnitude with quotation mark. We define the scalar projection of vector A onto the direction B by. So now we just use the first four letters. Scale. We have subindex B indicating the direction. A is the vector that we start with. And so basically we just take out that purple circle part, which is A dot B over the magnitude of B, which is exactly that magnitude portion, okay, of your vector projection. Alright. Okay. So we have this quotation mark magnitude because this quantity may be negative. So you see, the only problem here is that cosine value could be negative, could be positive, right? So the absolute well, the magnitude of A, the magnitude of B, they're all non-negative. Remark. So basically, if you take the magnitude of projection of A onto the direction of B, and then what you do is you take the magnitude of final expression right here. So I'm gonna still keep the bracket to represent the scalar in front of a vector. So now, so basically, what's inside the curly bracket is a round bracket is a scalar, but it's possible that it's negative. Okay, so if we want to take it out, we just want to make sure that the number that we take out is something non-negative. So we can take out the absolute value of that. Okay. And then what's left inside the magnitude is the magnitude of B. Okay. So this is something slightly different from what we have done earlier. So if you recall, so when we talked about the unit vector B over the magnitude of B, right? So recall, so here this is a quick reminder of what we have done. So if you take the magnitude of B over the magnitude of B, so the magnitude of B in the denominator is always non-negative. Okay? And oh, of course, if you can divide it, then it's always positive. So that thing you can directly take out as a scalar. And since it's always positive, then you don't really need the absolute value here. Okay? But then you see, okay, the numerator and the denominator they are the same, so essentially this is the one. Right? But here the thing is always positive, so that's really nice. You can take it out directly. So what's slightly different here is that this thing, well, the inner product A dot B could be negative if the angle is too large. All right. Still, we can simplify because we know, okay, the denominator is a square, right? And it's a positive number squared. So you can take that out of the absolute value. So this is essentially the absolute value of the dot over, okay, we have in the denominator, we have the magnitude of B squared. And in the numerator, right here, we have the magnitude of B. Okay, that can be simplified. So essentially you have the magnitude of B. Okay, and you see, okay, so this is the true magnitude of the vector projection. And that is exactly the absolute value of the scalar projection. So this tells you sometimes that scalar projection could be different. That scalar projection could be negative. Since the dot product can be negative, might be negative. Right? Okay, so example. So let's look at the vector A, which is 2, -3, -1. And vector B is 1, 1, 2. So given the two vectors, we're able to compute these quantities. So in particular, we calculate the scalar projection of A onto the direction of B. So we can just apply the formula, right? So the scalar projection is, so in this situation, we just use the first one, because here we have A and B explicitly defined in terms of the components. So we don't really have to calculate the angle, we just need to utilize the dots. Okay. So the dots over the magnitude of B. So the dot product, so we just need to realize that we just multiply the components. So the first component multiplied is 2 times 1, plus now the second component multiplied is -3 times 1. And the third component is -1 times 2. And then we add up. And then the magnitude of B, right, is the square root of the components of B squared. So if that's good, then the calculation is going to be straightforward. It's 2 minus 3 minus 2, that's -3. And the square root is 4 plus 6, 4 plus 6. Okay? And in this situation, you don't really have to simplify. So that's what you mean. And then you see, okay, indeed, this is a scalar projection that's negative. That just means what? That just means, okay, so if we want to do the vector projection, it's gonna be along this direction. But we are just going the opposite direction of B. Right, so because this scalar projection is negative. Remark. If the scalar projection okay onto B is non-negative, then the magnitude of the vector projection onto B of A is exactly the scalar projection onto B of A. And to sketch the figure, it just tells you that the A and B, the angle between them is less than pi over 2. So the vector projection is exactly this vector. Should be okay. And here the length is exactly the scalar projection onto B of A. When this value is positive. So basically, this is saying, okay, so if I have this direction B pointing towards the right, and then I, in a way, you can think about it as a real line, right? And then as long as your scalar projection is positive, then you will just stay on the right-hand side of the tail of vector B, right? But then if we are in the other case where the scalar projection is negative, that just tells you the angle is a little bit too large. And then when you sketch the projection down to the direction of B, you eventually hit the negative side of my original vector B. So we have this portion pointing towards the negative direction of B as the vector projection onto the direction of B. Okay. Okay. And in this situation, the length is the negative of this scalar projection onto B of A. Since this quantity is negative. I think a little bit more space between these two figures. So it's good. So that's actually the last comment of this section.